Last time we talked about sequential decay, which occurs when a radionuclide decays to another radionuclide. In this lesson, we will discuss 3 cases of sequential decay and attaining equilibrium. Equilibrium is achieved when the rates of decay of the daughter and the mother are equal. Let us start with the case in which the half-life of the mother is shorter than the half-life of the daughter. In such cases, the mother will just decay to the daughter, but they cannot attain equilibrium. In cases where the half-life of the mother is longer than that of the daughter, mother and daughter can achieve the so-called transient equilibrium. For transient equilibrium to be attained, the decay constant of the daughter needs to be about 10 times that of the mother. In cases where the half-life of the mother is much longer than that of the daughter, the mother and daughter will attain the so-called secular equilibrium. In the case of secular equilibrium, the decay constant of the daughter is at least 100 times larger than that of the mother. Keep in mind that distinguishing between transient and secular equilibrium is not always straightforward. Fortunately, for most activity calculations at a given time, selecting the wrong option will only result in minor differences. But how do we know when equilibrium is attained? In the transient situation, equilibrium is achieved at 4 times the half-life of the daughter radionuclide. For the secular situation, equilibrium is achieved at 6 times the half-life of the daughter radionuclide. Now let's have a look at the different situations and discuss some examples. In the case of no equilibrium, the parent decays so fast that after 5 to 10 of its half-lives, the activity or the number of atoms of the parent will be almost zero and only activity of the daughter will be left. Here is one such example. Tellurium-131 has a half-life of 25 minutes and will decay to iodine-131, which has half-life of 8 days. You can see in this plot that the number of atoms of the mother, Tellurium-131, is decreasing very fast, while the number of atoms of the daughter, iodine-131, is increasing and will exceed the number of mother atoms quickly. In transient situations, the activity of the daughter will grow until its decay curve is eventually parallel to that of the mother. Now let's have a look at the general equation that we have used to determine the number of atoms of the daughter isotope. We can modify this equation by taking exponential decay of the mother out of the brackets. After sufficiently long time, so when equilibrium is attained, the circle term will become 0, which leads to this simplified equation. This equation can be further simplified by replacing this term by the number of atoms of the mother, resulting in this equation valid for transient equilibria, which you can use to quickly calculate the number of atoms of the daughter at equilibrium. We can also modify this equation to determine the activity of the daughter by using the link between activity and number of atoms, which results in the following equation that links the activity of the daughter to that of the mother when transient equilibrium has been achieved. An example of transient equilibrium is the mother molybdenum-99 with half-life of 66 hours, which decays to its daughter technetium-99m, which has a half-life of 6 hours. Here you can see how this pair behaves in transient equilibrium. The activity of the daughter first increases, then gradually levels off and follows the activity curve of the parent nuclide. Now let's examine the case of secular equilibrium. Here the activity of the parent decreases so slowly that it appears almost constant, while the activity of the daughter steadily increases. Once equilibrium is reached, the activity curve of the daughter will follow that of the parent. To derive the equation that you can use for secular equilibrium, we follow the same methodology as for transient decay. The only difference is that since the decay constant of the daughter is so much larger than that of the mother, we can replace this term with the decay constant of the daughter. This results in the following simplified equation to calculate the number of daughter atoms. Similarly, the activity equation for secular equilibrium can be simplified to give a very simple equation which shows that the activity of the mother is equal to the activity of the daughter in case of secular equilibrium. An example of secular equilibrium is the radionuclide germanium-68 with a half-life of 270 days, which decays to gallium-68 with a half-life of 68 minutes. In the graphic representation, you can see that the activity of the daughter first increases, but levels off to match the activity curve of the mother. Thank you for watching. In the next lesson, we will discuss practical examples of sequential decay.